Welcome back to CSE 373. Today, lecture 4, we're going to be talking about asymptotic analysis. And this is something that we've seen a couple times already in this course where we talked about complexity classes and big O notation. And a lot of the times what we've been talking about so far has probably been a little unsatisfying or maybe a bit confusing because we've been waving our hands around a lot. And so today's lecture is really about kind of diving in and understanding the more formal and more rigorous approach to doing this. Part of it is to show you that the intuition we've been using so far is correct, but also as a tool for when our intuition doesn't quite work out anymore because we start handling more complex cases. One thing I'll note, sometimes it's really hard to tell a story about this in a very linear fashion, where here's the first thing, and we introduce all the terms you need before moving on to the next thing. Sometimes we have to revisit things a couple times. And so today's lecture and Friday's lecture, and we'll even start to still be talking about this next week, we'll start filling out some of the story if things don't quite make sense yet. So don't worry if you get hung up on a couple details. We will be talking about this stuff a lot. But before we dive into what today is going to look like, I have a few announcements. So Project Zero is due on Wednesday, so the day of this lecture, at 11:59 p.m. And we're also releasing Project One the same day. As a reminder, there are multiple options for you to work with partners. You can choose a partner on your own, maybe someone you know or someone you've just met in class. We sent an email about the partner pool where you can sign up and we will assign you a partner, or you can work alone, which is not recommended by us, but you can do it. One new announcement is that exercise 1 is going to be released this Friday, and we're generally going to have kind of a schedule where we have weekly-ish exercises at the same time in the projects where you get to focus more on the conceptual work and practice these things. The stuff that we're doing in quiz section and in lectures where we do these practice problems is going to be really helpful for those exercises. One last thing, you saw an email about this, but we have the option to choose your breakout rooms for the class sessions. Please see the end announcement for details on how to sign up. And as a reminder, you can change these groups at any time. But so today's class, Wednesday's class, is going to be the first one where we have these pre-assigned rooms. And if you don't know anyone quite yet, that's totally fine. We'll still use random assignment for those that didn't sign up, but we encourage you to just join a group on Canvas for these lectures. Okay, so what are our learning objectives for today? After this lecture, you should be able to describe the difference between code modeling and asymptotic analysis. These are components of what we call algorithmic analysis. You should be able to model a simple piece of code with a function describing its runtime, and honestly, we'll still actually get to some more complex ones soon. And explain why we can throw away constants when we compute big O bounds, both from the practical perspective, why it's okay for us to use this as a tool, and that's something we do, and from the perspective of the definition of big O, which we'll introduce today. One thing I'll mention is one of the things we'll do towards one of the last videos for today is we will start doing some proofs or talking about some proof strategies for big O. Notice that doing these proofs is not part of today's learning objectives, so don't worry if that is a little confusing. We just want to show you these proofs as a way of giving you some intuition for why we can throw away constants, but it's not part of our learning objectives, so don't worry if it seems a little confusing. We'll talk about how to do these quite frequently. So here's the outline for today. In this video, I'm going to overview kind of some things we've seen so far and reviewing some concepts and setting up kind of the picture for the rest of these videos. And then the next 3 videos, we're going to talk about these things called code modeling, asymptotic analysis, and the definition of big O. Okay, so let's go through it. So on last week, when we were doing a review of some 143 things, we introduced the idea of a complexity class. A complexity class is a broad category that we can put algorithms into based on their efficiency and the relationship of that efficiency to the input size. And so we highlighted some really important complexity classes: the constant complexity class, the linear complexity class, and quadratic. So we've seen these terms and we haven't fully defined what they mean. And today is going to be, in some sense, kind of a prequel to this slide, where we're going to introduce where this terminology comes from and how to derive why it's okay to put a function that takes 2 n steps and one that takes 10 n steps in the same complexity class, the linear or O of n class. That's kind of where we were. Now, let me talk a little bit about why we're going to be talking about this. why go through all this process of having some tools to analyze our code? Here is the slide that should look a little bit familiar, at least this table. But now we've added this big O notation to both the array list and linked list implementations of the list ADT for how long they should take in terms of runtime. So complexity classes for operations help us differentiate between data structures. It lets us decide which data structure is better in this context and why. And so far, I've been using a lot of hand-wavy notions where I say, well, like for this data structure, you only have to change the first node versus this other data structure, you have to change every element, which in English is clearly different, right? Changing first node sounds a lot easier than changing every element. But if you ask me why is that the case, I'd be kind of hard-pressed to give you an answer, to tell you why those things are different. And so one of the things we're going to do is, in our more formal approach to this, is come up with a definition, in some sense, why changing the first node is more efficient than changing every element. And in order to evaluate data structures, we need to understand the impact of our design decisions, knowing when I use this data structure, when is it going to excel, and when might it be slow. Okay? And so this big O analysis is supposed to be a tool to help us make these decisions, and we want that tool to be rigorous. Now, let me mention that this algorithmic analysis that we're going to be doing today is just one tool. There are many possible tools you could use, and this is just taking one perspective. Now, why do we choose this tool out of all the possible tools we could use to analyze our code? Well, I would argue that there are three main goals that are working that we want in a tool for analyzing our code that make big O analysis or algorithmic analysis a really great candidate. We want this tool to be simple, firstly. We don't want to care about tiny differences in implementations if they really aren't going to have a big impact. We want it to be able to describe something at a high level and big picture. And another meaning of the simple description is we want it to be describable to many people. We don't want it to be that you need a PhD in computer science in order to understand this stuff. We want to be able to make it understandable to a broad audience so it could be used as a good communicator. A second goal is we want this tool to be mathematically rigorous. We want it to be precise and be well-grounded. The reason we want rigor here is not because we were trying to make it hard, because we want to provide some sense, a flexible basis for you. So when you go and find examples that don't quite fit in with the intuition you've built up already, you can always go back to the definitions and derive something yourself. So we want this to be rigorous to work in more cases. And lastly, we want this tool to be decisive. We want to produce a clear comparison when indicating which code is more efficient or which one might take longer. And so these three goals we'll come back to is why Big O helps us achieve all three of these things. So as a bit of review, let's talk about where we've probably seen this so far and how is this going to look different in 373. So in the 143 discussions of Big O, we use general patterns or intuitions to help students understand this process. We usually say something is O of 1 or constant time if there are no loops. We'd say it's O of n if there's one loop, O of n squared if there's nested loops. And let me tell you, this is not a useless intuition. It's actually very useful in practice, so you don't have to go rederive things from scratch. But in 373, we're going to go into more depth, first to explain, in some sense, why these intuitions work, and so that this depth, as I mentioned, forms a basis for handling more complex cases when they arise. And these complex cases will arise even in relatively simple code. And it will also arise in complex code, and we'll talk about both of these. So in some sense, in the 143 world, we kind of had this process where we took code and somehow magically using these intuitions came up with a big O bound. In 373, we're going to take a much more principled approach. So before I describe what's going on in this slide, let me mention one thing. The terms we're going to be using in this class to describe this process are not necessarily standard. Usually when people say algorithmic analysis, they might mean one of many things. They might conflate algorithmic analysis with this other tool called asymptotic analysis that we'll describe. But we're going to be a little bit, or try to be a little bit more precise in giving concrete names to processes that are important. And so when we're talking about algorithmic analysis in 373, we mean this whole process, this whole pipeline of going from code to a complexity class. But this whole process actually has some concrete steps. So we start by thinking about starting with your code, which I have visualized as this pink code block. And I have an example of a for loop with 2 steps inside of it. The first part of algorithmic analysis is what we call code modeling. And code modeling is a process that takes code and turns it into a function that describes the runtime in terms of the input size. So and I'm going to hand wave for a second because we're going to have a whole video on code modeling, and we'll come back to more complex code modeling later. But we start with this for loop, and we somehow have a process that turns into a function that says, hey, for any input size n, this code will take 2 n steps. So this code modeling is the first step of the algorithmic analysis process. Then once we come up with that function describing its runtime, we can now apply asymptotic analysis, which takes a function and puts it into this broad complexity class, in this case, O of n. And for us, it's going to be important to separate these concerns, coming up with a model for your code and then using asymptotic analysis on that model, because it allows this process to be more flexible. So in our context, we're almost always going to be talking about, for code modeling, runtime. So modeling the time it takes, approximately how long it takes, for something to run based off its runtime. But that's not the only thing we care about in terms of efficiency. Remember, we might care about how much memory your algorithm takes up, or how much energy it uses, or really anything. And by separating algorithmic analysis into these 2 steps, we now allow it to be more generic. Because now you could say you can model anything about your code, maybe how much memory it uses or how much energy it uses, and come up with a big O bound for those because we've separated the concerns. We'll come back to examples and kind of defining what these actually look like and how to do them in the remaining videos for today. So again, as an overview, the remaining videos, the next one is going to talk about code modeling. What is that? How do we do it? Then we'll talk about asymptotic analysis, that step of coming up with that complexity class. And then we will talk about some definitions for big O.